Hi everyone, Miss Colasso here. So I am making this video to walk you through the 3.3.5 practice on Apex. I'm going to go over each question, kind of discuss them, and maybe do a few problems out for you guys. Okay, so we'll just get started with the very first question. So it tells you to draw a lake and label different regions or different zones within the lake. I put this picture on Google Classroom, but now I've also embedded it in our website. So I'm going to ask you really just copy and paste it. That way you don't have to mess around too much with the drawing feature in Google Docs, or you don't have to manually draw it. I think this picture is sufficient where you could see each zone pretty well. So I really like this image, so I would definitely use that. So that's going to be there for you already, easy peasy. Okay, so number 2, why do overlapping niches lead to competition? So I want you to remember the definition of a niche, right? It could kind of be considered as the function of an organism, just something that they take on, something that they do, their role essentially in the ecosystem. So if you think about it, when organisms are overlapping in those roles or functions, they have to compete because there's going to be a limited amount of resources for both of them or for many of them. So that leads to competition for resources. Okay. Number 3, after an extreme disturbance, what kind of organisms move into the area first? So this is when, an extreme disturbance could be like a flood or a tornado or a hurricane or a wildfire, something that's going to take out a lot of organisms. So the very first ones to move there are going to be small, fast growing, ones that reproduce very quickly and could withstand severe environmental conditions. So some examples of these could be like a lichen or a moss, just because they also do photosynthesis, so they could produce their own energy, and they're small and very fast growing. Okay. Number 4, the graph below shows the population of a species over time. So you get this blank graph, and then it asks you to label 4 parts of the graph. So I'm just going to show you how we label them. This is my suggestion. I would go in and give each one of these a number. So kind of just go 1, 2, 3, 4. And that way, when we edit the graph, all we have to do is put numbers to correspond with how we've labeled it. So now let's make this a drawing so we know how to do that. We're going to copy, insert, drawing new, and then we're going to paste. Okay, I always like to make it a little bigger. Okay, so we have our first one is exponential growth. So we're going to put a 1. You could shade it in so that's easier to see. And we're going to put that here because this is where it is mostly growing. Okay, I don't know why it's not letting me. So you could keep it over here so we see that exponential growth. And I want you to save and close. Okay, and then see, you could continue editing it. So the next one would be maximum growth. Okay, so let's go back and edit. So we're going to put a 2 near this black dot because that's indicating the maximum growth. So again, same thing. You could even use a different color if you'd like. And there you go. Now, the next one is carrying capacity, I believe. So let's just save and close and double check. Yep, carrying capacity. So in any graph you're going to see where it's comparing the population size and time or resources, that carrying capacity is always going to be this red dotted line. So we could put a number 3 right here. And then let's color that in another color. Easy. The last one is where the growth is beginning to decrease. So that might look a little confusing, but it's actually this area here, because see how this first part leading up to the black dot is kind of that exponential growth? Now it's starting to decrease and plateau once it reaches carrying capacity. So we're going to put a 4 right over here to indicate that. And you could choose any color you'd like. Okay, so we're going to save and close. And there we have it. Okay, so that's how you're going to do this question. So a follow-up on that is, why does the growth slow down? So think carrying capacity means this is the amount of resources available for a population that they could survive on. So as they reach the carrying capacity, the total amount of resources, the population is going to start decreasing because they're hitting that point where there's not going to be enough resources for them. Whereas here, they have plenty of resources. There's a wide range between the carrying capacity. Okay? So this is where there's a large population size but limited resources. So inevitably, the growth will slow down. So organisms start competing for those resources. What are the conditions for exponential growth? So it would be unlimited resources. So like I mentioned here, they're growing because they have so many resources. Okay? Moving on. So number 5, a plant can either have smooth seed P or rough seed Q. Rough seeds are recessive and smooth seeds are dominant. In a population of 100 plants, 32 of them have rough seeds. So I will say that I put a Hardy-Weinberg problem video on our Google website, and the problem that I solved in the video and demonstrated was very similar. Instead of 32, it was 30 out of 100. But I'm going to show you how to solve it with this exact problem. So we're looking for Q squared. So Q squared is going to be 0.32 because Q squared, and actually let me open up my little whiteboard. So let me just move this aside. Okay, so let's see. So Q squared, just bear with me, equals 32 out of 100. So put that in your calculator, you're going to get 0.32. Okay, so that's Q squared. Now, if we want to get Q by itself, we have to take the square root of this, because if we just, set it out to make it look nicer, if we have Q squared equals 0.32, to solve for Q by itself, we have to take the square root. So this is something you may have learned in algebra. So now we have Q by itself, not squared, equals. And now I know you're going to think, why is it larger? That's what happens with decimals, okay? So this is going to be correct. So you're going to get 0.57, okay? So now what is P? So that's going to be easy to solve if you just remember this equation. P plus Q equals 1. Now we're just basically going to plug and chug like you would with any other math problem. So to solve for P, we already have our Q. So we're going to plug that in, and essentially we're going to do 1 minus 0.57, and that's going to give us P, which is going to equal 0.43. So now if you want to check your work, all you have to do is that Q value, 0.57 plus 0.43, and that will give you 1. So that's how you solve for P also. So now moving on to part D, it's asking a very similar thing. So there's 19 plants with rough seeds in a population of 100. What is the allele frequency? So now we know how to do it again. So that Q squared, 19 divided by 100, 0.19. Then you're going to take the square root of that. Remember, the value is going to be larger. So now you have 0.44. And then same process. So you're going to do 1 minus 0.44 to get the p-value, which is 0.56. Okay? So it's definitely good to practice these problems. If you find yourself struggling here and this wasn't helpful enough, feel free to watch my initial Hardy-Weinberg problem video, and that really goes step by step and breaks it down really nicely for you. Okay? But we're going to move on. So number 6, a species of rodent can either have brown fur or white fur. Brown fur is recessive and white fur is dominant. Which of the following would cause the rodent population to not be in Hardy-Weinberg equilibrium? So on our Google website, I put all of the conditions for Hardy-Weinberg equilibrium. So when you look at those, you're going to be able to fill in this chart just like you would as a drawing, and then you make text boxes in each one of these areas. So the first situation is brown fur allows rodents to hide more easily. So this would not cause it to be in Hardy-Weinberg equilibrium. So it asks in Hardy-Weinberg equilibrium. So that would be no, because that affects the selection, and in Hardy-Weinberg, we don't want that to happen. White fur attracts mates better, so same thing, we want random mating. We don't want it to be selected off of attraction or anything like that, so that would be no. Rodents cannot leave or enter their habitat. Yes, because in Hardy-Weinberg, we don't want any migration in or out of the environment. Rodents mate randomly. Yes, that's what I said before. We want it to be random mating. The rodents mutate a new allele for gray hair. No. So in Hardy-Weinberg equilibrium, we do not want mutations. Okay? So that's why it would be no. 7, how does adaptation affect the diversity of a species? So it actually makes them more diverse. Adaptations help to make them more diverse, more genetically different, because those traits are being carried on through each generation. Okay? How does adaptation affect the survival of a species and why? It makes a species more likely to survive because when a species has more variation, it can more easily survive changes to the environment. So think these organisms are adapting to changes in the environment, so that's going to help them survive, right? We think back to our peppered moths that we talked about, okay? So, the darker moths were able to blend in with the polluted environment, so that adaptation helped them survive more. How does adaptation affect the diversity of an ecosystem? So it also increases the diversity because there's going to be those different traits apparent in the ecosystem. How does adaptation affect the health of an ecosystem? It definitely makes it healthier. Adaptations are a good thing. That's what helps the species survive, so it's going to make the entire ecosystem healthier. Okay? So the last one, number 8. The table below shows factors that could be present in a population. Next to each factor, write whether it would cause natural selection or not. So an unlimited food supply? No, because there's no competition in unlimited, right? As we saw before, the population is going to grow exponentially. So that wouldn't really cause natural selection, survival of the fittest. Limited amount of shelter? Yes. Anything that would cause competition. So think limited amount of shelter. Certain organisms aren't going to have shelter. They're going to be exposed by predators. Then they're going to die. And that's going to cause the ones who found shelter to be selected for. Okay? Genetically identical population? No. So we want variation. We want change. Okay? Genetic mutations in population? Yes. That's what's going to help cause those genetic variations. Okay? No predators? No. Like I said, we want that competition. Predators are so essential for natural selection, right? So again, thinking about a peppered moth experiment or, the rock pocket mice, darker mice in a lighter environment are going to get selected by predators. So that trait isn't going to be able to pass down because the predators are going to select them at a disadvantage. Whereas the white mice in a light environment are going to be able to blend in and then they're going to be selected for. Okay, so predators are important for natural selection. Okay, and that is the practice. So I hope this helps. Please let me know if you have any questions about a specific problem. All right, bye guys.